We could have 12 million tons of crusts on the Seamount alone, round about 40,000 tons of rare earth elements. So in Germany, we import 5,000 tons of rare earth elements per year, a supply the German industry for 8 years completely with rare earth elements, only from this one seamount.
Welcome to the Elements of Deep Sea Mining podcast. Thomas Kuhn, geologist at the German Federal Institute for Geosciences and Natural Resources. Thank you for being here.
Yeah, thank you, Eric, for having me. It's a pleasure for me to join this podcast.
We met at the Seabed Minerals Conference a couple of weeks ago where you presented on the formation of manganese crusts, and that caught my eye. I learned a lot in your presentation, and I thought that would be great to have you on to sort of educate the listeners on that process, on what we know about what you've learned about how manganese crust formed. You've also, I'm interested, I guess, to start with in your expertise, your area of focus, and a little bit about what BGR actually is and does. I hear BGR get brought up a lot in the deep sea mining conversation, and I also don't know that much about exactly what is BGR and how BGR is seeming to be a government institute, but has exploration licenses or is kind of like in the role of a contractor in both hats. So that's a lot to start with. But yeah, tell me about yourself and how you got to BGR, I guess.
How I get into the BGR, is it correct? The right question?
Yeah.
Okay. Yeah.
Where did you study and how did you get to be a
scientist? Let's start with that. Okay, yeah, right. I'm a marine geologist. I would call myself like this. But I started studying geology and paleontology in the University of Freiburg, that is in southeast Germany. Actually, it was the former DDR, the East Germany. So I started my studies in East Germany. My original intention was to become a structural geologist, actually. So that was why I studied geology in Freiburg. But then in 1989, shortly before the wall came down, I went from East Germany to West Germany. So I fled, actually. And I ended up at the University of Clausthal, which is a little bit south of Hanover, where I'm based now. And there was a professor who deals with marine geology, with ore deposits, with marine ore deposits, actually. And when I came to West Germany, I needed the money, actually. And this professor offered a student opportunity to work with his working group. And it was by chance in marine geology, actually. So I started there. I felt it was a quite interesting topic. It was completely new for me, but it was a very interesting topic. And then I became the opportunity to take part in a research cruise. Actually, it was a research cruise starting from Okinawa in Japan and going through to Hong Kong. It was shortly after the wall came down, so for me, as a people of someone from East Germany, it was a really great opportunity to see a part of the world, actually. And this cruise really raised my interest in marine geology. And so, I stayed in this subject.
Amazing.
I did my master's degree or diploma, as it was called in Germany at this time. For this master degree, I went to England to the how was it called? The center. Now it is the National Oceanographic Center in Southampton. But at this time, it was called something different. It was based in Wormley, which was between London and Portsmouth, actually. So I did my master's thesis there. And then I did a PhD at the University of Berlin, Free University of Berlin, because my boss changed from Clausthal to Berlin. And he offered me to come with him. So I went to Berlin and did a PhD on hydrothermal ferromanganese crusts and hydrothermal sediments from the Central Indian Ridge. An area where I'm working now again.
The Central Indian Ridge. Okay.
At the Central Indian Ridge. So I'm now working. I'm working on both ferromanganese crusts, which I was talking about in Bergen, but I also work on hydrothermal systems in the Central Indian Ocean because BGR has one of its exploration licenses there. and I'm the manager of this license. And this actually was also the area of my PhD project. So quite interesting that there's kind of a loop which is closed now.
Yeah.
And then after doing my PhD, I had a postdoc position first in Freiburg again, and then at Geomar in Kiel. And in 2010, I changed to the BGR here in Hanover, and since then I'm working for the BGR. First 10 years, I was working for the Manganese Nodules project. I did the most of the geological work for our manganese nodule license in the Clarion-Clipperton zone. And then in 2020, I changed to the mesosulfide project in the Indian Ocean, which I'm coordinating, kind of leading since then. And since last year, we also have the Ferromanganese project, which is located in the Southwest Pacific Ocean. Yeah. So that was my past. So I mainly dealt with these three types of commodities, of resources on the seafloor.
Mm-hmm.
But I also in between I had positions dealing with the acquisition of an ROV, for instance, for the Geomar, the ROV Kiel 6000. I was the manager of this project for a couple of years. So I also have some experience in managing projects. But my focus and my main interest is in this typical classical marine geological work.
So you've been working in this field for what, 30 years?
Yeah, 30 plus, yes. Mm-hmm.
And how have you seen the conversation, the public attention to deep sea mining develop over that time? Has my assumption is that there's become more attention to it, and that has led to more pushback. And I just wonder how you would characterize the development of the kind of public debate or public conversation.
Yeah, in the 90s, deep sea mining was not a topic at all. At least not in Germany, okay, I must say, or in Central Europe. When we try to get projects, we are not allowed to say deep sea mining, so we had to circumvent somehow this, and we try to understand geological and geochemical and geophysical processes in the deep sea. To understand the processes, and we did not do research with respect to a mineral deposit or mineral deposit formation, or with respect to deep sea mining. It was more deep sea research. That was when I started. So it was deep sea research, and I think it stayed like this maybe until the last 10 years at least. Deep sea mining became a little bit more an issue in the pub or in the news or in the media, but at least in Germany, publications with respect or in this direction was all about environmental risks and environmental problems that might be caused by deep sea mining. Or the public perception was always into this direction. Only until recently, I would say. Only until recent 1 or 2 years. But until then, in the public, even when I was on a party and was talking to friends, and they asked me what I do, and I was talking about deep sea exploration, the first question always was, "Oh, don't you destroy everything down there?" So it was kind of public perception of this topic, and it changes. And when you look in media, when there was reports in the newspaper or whatever, it was always that there was the discussion about the risks and not the opportunities. And this is very slowly changing a bit since the last couple of years. Maybe I would say actually to have an effect or to realize an effect about this is the last 1.5 years since we have a new government. But even after Russia was including the Ukraine even then there was not really a change. It's only happening now slowly that in the news, in the media, they discuss both the chances and opportunities and the risks. So it's starting a little bit like this, but that's only very recently. Until then,
I noticed that recently the general public, the general news, producing organizations anyway, have started to understand critical minerals a bit and how important minerals are. So I wonder if that allows a little bit of a change in that direction, because we've all understood environmental damage for a long time. And so when you see a new industry that's going to go into a new ecosystem and disturb it, it's easy to, and I think it's quite natural that a lot of people react with kind of a fear and a hesitation, and we're just humanity repeating our same mistakes over and over here, somewhere new and somewhere pristine. And so I wonder if it's a little bit that obviously it's a balance. And I'm very interested in the trade-off aspects of this question. And so I a little bit wonder if now people are just becoming more aware of the other side of the balance a little bit.
Yeah. I mean, this, another reason, especially which holds true for Germany, is that we have closed all our mining sites in Germany. The last one closed in 1992 for metals, for metal mining or ore mining. So we don't have this kind of mining in Germany anymore. And when there's report about mining abroad, it's mainly about when there is an accident. When there's something happening. So mining has a bad reputation in our society. And the other point is that all the things that surround us, where metals matter, are so normal to us. So they are just there. We don't think about where all this stuff comes from. Because we don't see where it comes from.
Yeah.
And so mining is very far away from us. And it was just normal that these things are available.
It's kind of like how food just shows up on the grocery store shelves, and we don't learn about what cows and pigs and chickens are like.
We only learn it when this chain is interrupted, or there's a danger that it might be interrupted. It started with Corona, and it continues with the war in Ukraine, and now with the war in the Middle East.
Yeah, for sure. The other thing that I thought was really interesting, I guess your fourth point about the stability and resilience of the ecosystems. That's something that I haven't heard before. And I have heard people say that I've heard this discussion about how stable things are. And obviously there's often this idea of recovery over human timescales or recovery over geologic timescales. And so it's a bit interesting. I think you're the first person who's kind of articulated that the natural cycles, the natural disruptions occur not necessarily over human timescales. So it raises the question of what is the right timescale to be considering these things in. I was having a conversation yesterday with a philosopher, an environmental philosopher named Brian Norton, whose work focuses a lot on what scale do we look at environmental problems in. And I think it's interesting that because it often seems kind of like a knockdown argument. There's going to be no recovery within human timescales. And then it's interesting you raised the question of what is the right timescale that we should be thinking. And if the natural variation happens over non-human timescales, then that's an argument that maybe we should be thinking over longer terms.
Yeah, I'm definitely thinking like this. We have these three different types of deposits, and they follow different timescales, I would say. So with the hydrothermal systems on mid-ocean ridges, with these active hydrothermal systems, there is natural change, which is definitely within a couple of years, so within the human timescale. And so we see the activity of hydrothermal fluids emanating from a black smoker changes within a couple of years. It starts forming it reaches a kind of a maximum and can die within a couple of years, maybe a couple of tens of years. But we also have avalanches, we have earthquakes, and so on. So this, I think, a hydrothermal system and variability within a hydrothermal system is at least partly within a human timescale. But it's definitely different with the manganese nodules. So the timescales with the manganese nodules is much longer. So you can see that when you look at the sedimentation rates. Sedimentation rates in the Clarion-Clipperton zone are some rates around 1 centimeter per 1,000 years. So when you pull something through the seafloor and you produce some pluff tracks on the seafloor, and they are 20 centimeters deep or whatever, it's no wonder that you see them after 50 years. So when I read in the newspaper, you can still see these pluff tracks which were made 50 years ago, and you still see them. Yeah, of course, it's totally normal. So that's why I think we have to think of it in this larger time scale. So another example, Clarion-Clipperton zone in the BGR license area. There's one area covering several tens of square kilometers where the upper 700,000 years of sediments are missing. They are just not there. So the seafloor is 700,000 years old. When you go a little bit further, the seafloor has the age of today. So what I want to say is we have a significant erosion in this area. But this is 700,000 years. So it's a very long time scale. Then other things that happen in this area are big landslides. So there is a sector collapse of one of the large volcanoes in the BGR license area. The volcano is about 2,000 meters above seafloor, and there is the northwestern flank was collapsed and produces a big landslide, which went into the deep sea just northwest of the Seamount, reaching 20, 30 kilometers, covering everything what is in its way. We see other smaller, but this slumping, we cannot date it, but it's certainly a couple of, maybe even a couple of million years ago. But on the other areas, we see small landslides which happened recently, which also cover not a large area, but they still cover an area. So there are quite a number of naturally processes occurring in this area, and the ecosystem can cope with that. And when we plan to remove parts of the manganese nodules, and when we do this in an intelligent way so that we maybe mine only rather small areas and we leave nodules behind so we don't take away all the nodules, I think the natural system can cope with that.
Fascinating.
Yeah. So this this is something that I really miss in the public conversation.
It's difficult to say. As I said, here I think we should at least investigate the natural variability. So what we can do is to find the reason why we missed this 700,000 years of sediment in the BGR license area. What's the reason for this? Yeah, and where has the sediment go to? So why is it missing? That's something we can do. We could also date the slumpings, or at least try to date the slumpings that we have mapped in the license area. So this is something we can do. What my colleagues are doing are the investigation of the actual currents and near bottom currents. So we should investigate what is the effect of the actual currents on the sediments. Will there be eroded, or under which current conditions sediments can be eroded, and under which they will be really sedimented? So that's something I suggest could be done to understand natural variability, at least within the context of currents, of sediment transport and sediment deposition. And this is something I don't see. I mean, on the other side, I only watch the manganese nodules community from the side because I'm not in anymore. So maybe I missed something. But I brought up this discussion last year on our annual symposium at the BGR. There's an annual symposium about the exploration work within the manganese nodules and the massive sulfide exploration licenses. And we invite our contract partners within this exploration work, but also other scientists to join this meeting, and we discuss actual developments. And last year I brought this topic, but I couldn't find any. I didn't get any resonance. So I was a little bit overheard, I would say, and thought, okay, this is something I'm really missing, actually. Yeah.
Well, that's, I mean, coming from the, more looking at this from the more philosophical question of like, values and what sort of timescales should we be considering when we're making our decisions? It's suddenly extremely interesting to think that, well, an input to that values discussion would be the scientific understanding of the timescales over which natural variation happens in these places, and that we can. I'm always looking for places where the sort of philosophical discussion can be informed by the scientific, by more scientific research. That's something that I think philosophers often miss, is like, where can I look for empirical evidence to inform my thinking on things? So that's fascinating.
So maybe one should do a literature review into this topic. Maybe I'm missing things, that could be, but that is my impression, that that this part of the discussion is missing. So yeah, maybe this is something we could initiate. That we should really look at to investigate what are the time schedules on which those systems recover naturally. Because there are these natural changes, definitely.
And it's going to be different for different. I mean, this is another thing. It's so easy with the deep sea mining conversation to either try to make it kind of one thing. We shouldn't ever deep sea mine anywhere because it's going to be very slow to recover. And also that the nodules conversation tends to dominate. So
yes, that's it is different for different commodities, different types of seafloor deposits. That's for sure. I just talked about the massive sulfides, where the time frame for natural variability is much smaller. It's probably within human time scales, human scales. And with the crusts, it's different as well. So to name another example with respect to the crusts, we had a research cruise last year to the Louisville Seamounts in the Southwest Pacific Ocean, and we found a lot of dead corals on the Seamount summits, or on the transition from the Seamount summits to the upper slope areas. A lot of large coral colonies, which most of the corals were dead. So then I was researching a little bit, and I found some literature from colleagues from New Zealand who found the same phenomenon on other seamounts on the Louisville Seamount chain. And they dated these corals, the dead corals, and they found that they might have died around 10,000 years ago, roundabout. It was the end of the last glacial period. So when there was a global warming. So obviously, those corals could not cope with the natural global warming. And they have not recovered in great amounts until today. There are only, on this large colonies of dead corals, there were only a few living ones. But we speak about, we speak about 10,000 years, but on the other side, the natural variability happened within a few hundreds, maybe a few thousand years. And in this case, the natural system could not cope with, because the changes maybe were too quick.
Yeah.
So this is natural variability. This is what's caused by nature.
Fascinating. Okay, well then, I guess it's time that I move us on to the actual topics that I had reached out to you to discuss. So let's start with formation of crusts. I guess I'm just going to kind of hand it to you to give a little 101 primer on what we know about how crusts form.
Yeah. So we speak about ferromanganese crusts. These are thin encrustations on hard rocks on the seafloor. They have a thickness between a few up to 15, maybe 20 centimeter thickness.
Mm-hmm.
In some locations, we even have up to 50 centimeter thickness of these crusts. They consist of iron oxides and manganese oxides. Their major occurrence is along seamounts. Seamounts are volcanoes on the seafloor, which rise more than 1,000 meters above the surrounding seafloor. There are round about 50,000 of these seamounts along the on the seafloor of the different major oceans. Sorry, so 50,000, which already indicates the significant potential of these crusts because they occur more or less on all of these seamounts. These crusts form because on the seamounts, deep sea oxygen-rich currents can rise along the slopes of the seamounts. So in the deep sea, we see oxygen-rich currents which move over the seabed along the deep sea ocean floor. These currents or these water masses are a couple of 100 meters thick. They are oxygen-rich, richer than the seawater above it. And on the seamount flanks, these currents, they can move upwards. And this way they can mix with water layers further up in the ocean column. And there is a so-called ocean minimum zone in the ocean water column, which occurs between 500 and 1,000 meter water depth. And in this oxygen minimum zone, there's an increased amount of dissolved metals, mainly iron and manganese. And when along the seamounts, these oxygen-rich water from the deep sea can mix with the oxygen-depleted water, the oxygen minimum zone, the dissolved iron and manganese oxidate and precipitate as manganese oxide on the seafloor. And they do this, they are precipitate on the seafloor when the seafloor is a hard rock. When it is a soft rock, then manganese nodules would form. But normally on the seamounts, especially on the seamount flanks, there is no sediment because of the currents. The currents remove sediment or the steepness of the slope, which cause sediments just to slide down. So that's why on the rather steep seamount slopes, especially on the upper part of the seamount slopes and on the transition to the seamount summit areas, we find this ferromanganese crusts. This is a very slow process. These crusts grow with grow rates between 1 and 5 millimeter per million years. So when we have a 10 centimeter or 100 millimeter thick crust, we can have tens of millions of years which have passed by before this crust form or during this crust form. The manganese and iron oxides, they have a surface charge. Manganese oxides have a negative surface charge, and iron oxyhydroxides have a positive surface charge. And other metals in the seawater are dissolved as positively or negatively charged ions. So copper, nickel, cobalt are cation, so they are positively charged, and they adsorb on the negatively charged manganese oxides. And other elements which are form anions in the water column are adsorbed on the positively charged iron oxyhydroxides. And these oxides, manganese iron oxides, they have a very large surface area, up to 300 square meters per gram material. 300 square meters per gram oxides.
What?
300 square meters per gram. So it's quite large. Yeah. And this is the reason that this low process at the large surface area is the reason why elements can be enriched up to the factor of 1 billion over seawater. So this is the reason why we have cobalt, for instance, up to 1% in the crusts and only 1 or 2 nanomole in the seawater. So this is a difference of 1 billion roundabout. So we have a very strong enrichment of these metals in the crust over the seawater. And we speak about metals like cobalt, rare earth elements, platinum, tellurium, and phosphor. These are the major elements which occur in the crust.
Why those elements? Like, why cobalt and not nickel?
Nickel is also enriched, but not to the same degree. The reason for cobalt is dissolved in a 2-valence state in seawater, 2 plus, as a cation with a 2 plus charge, twice positively when you want. When it is adsorbed onto the surface of the manganese oxide, it's first adsorbed as a 2 plus ion. As a 2 plus ion, but it can also go back into solution. So there's an adsorption-desorption equilibrium on the surface of this manganese oxide.
Okay.
The same happens with nickel. But cobalt, when it is attached to the manganese oxide surface, it will be oxidized to cobalt 3 plus in a 3-valence state. And as cobalt 3 plus, it is not dissolvable in seawater. So it cannot go back into solution. So as a cobalt 3 plus, it will be included into the crystal lattice of the manganese oxide, and it cannot go back into solution. Whereas nickel will not be oxidized. It stays as a nickel 2 plus, and it can go back into solution. So there's adsorption-desorption equilibrium between most of the elements, and they only adsorb on the surface when there is a surface place, a surface site available for them. When all the surface site, manganese oxide has a number of surface sites, and when they are all covered, nothing happens anymore. But with cobalt, it's different. Cobalt will be included into the mineral lattice of the manganese oxides, will not occupy a surface site anymore. So there will be a new surface site.
Oh, really?
Which can be covered by any element, including cobalt. And over time, this way, the cobalt is relative to the other elements more enriched than the other ones because of this oxidation process. This is also called oxidative scavenging, this process. And it happens for some of the elements, like cobalt, like cerium, for instance, also doing this, thallium, tellurium, platinum. And these elements, this way, are more enriched than other elements. The other elements are also in the crusts, but not to the same degree. Actually, you find the whole periodic table in the crusts.
Yeah.
But certain elements which are going through this oxidative enrichment are more enriched than others. And cobalt, for instance, belongs to that.
This is fascinating, and this is exactly why this is much more than I managed to glean from your presentation at the conference a few weeks ago. So, and this is exactly why I wanted to hear from you, because I had kind of just a very simplistic model in my head that, well, there's all these things in seawater, and there's some mechanism that they precipitate out of seawater, and that they happen on Seamount essentially just because of the sedimentation thing, that they're going to happen anywhere that they don't get covered by sediment. And so when nodules, there's low sedimentation rate, it happens slowly there. On Seamount, there's no sedimentation because the sediment's falling off. And so, but sounds like there's so many more mechanisms here. So the first one that I picked up was there's this updraft of water going into this from the oxygen, kind of the low oxygen to the higher oxygen zone. This reminds me of how on the west coast of North America, all the precipitation dumps out as the air mass gets pushed up these mountainsides. Except here it's not that there's some sort of a expansion happening to the water. It's that they're oxidizing out because suddenly they're encountering an oxygen-rich environment, and then they react with the oxygen, and then But that's only for that's just the process for the iron and the manganese, essentially. Then for the rest of the elements, there's this other more, what I think of more chemistry process of ions and valences and being.
It is because iron and manganese are the major phases in the crust. They are. So we have about 25% manganese, 15 to 20% iron in the crusts, and the interesting elements in terms of deep sea mining, they have contents between 0.1 and 1%. So they are much less concentrated in the crust. So we have these major phases, and then most of the processes are just surface chemistry. Because of surface charge. The processes are mainly controlled, not completely, but mainly controlled by surface charges, adsorption, desorption processes, and then oxidation processes for certain elements on the surface sides. That's what happens.
And then I guess you'll have different concentrations of minerals in the seawater in different locations. So does that create different mixes in the I guess one question is, like, I assume that the reason that they're predominantly iron and manganese also has to do with that there's just more iron and manganese in seawater than there is other elements. I assume that that's part of it.
Yes, there are certain changes in the water column. I would say they cause different growth rates. I think the growth rate is controlling at least the concentration of most of the minor and trace elements rather than a change in the water column. It's more the growth rate that controls the content of the minor and the trace elements. The major elements, manganese and iron, this is more a matter of the content in the water column. That's correct. And there are changes. That's true. These changes, especially for manganese and iron, and these are, for instance, controlled by the distance of the location from hydrothermal ridges or from mid-ocean ridges, because a significant part of iron and manganese is introduced into the ocean by hydrothermal activity on mid-ocean ridges.
Really? I would have assumed that they are coming in from runoff from terrestrial sources.
That's the other major source. However, a large part of manganese and iron, which is from river runoff, is precipitating on the shelves or on the seamounts, on the continental slopes. This is because when rivers have a different chemistry compared to seawater.
Okay.
And when rivers enter the seawater, there's a kind of a chemical barrier where a lot of this material is precipitating and will not reach in the further ocean. So this is major source for iron and manganese. Most important one, I would say, are the hydrothermal activity on the mid-ocean ridges, and the second one is not by the river runoff; it's more by wind, aerosols that are transported by wind into the oceans. And rivers are also important, of course, because there are a lot of material precipitates close to on the shelf or on the continental slope. But of course, then there are also recycling processes which remobilize elements into the water column. This is also something that happens. But I would say, to my understanding, the major sources are hydrothermal processes. Weathering is also an important process of volcanic material on this on the seafloor, and the input of dust via wind into the oceans.
I love how every time I have one of these conversations, I just learn how infinitely more complicated everything
It
is
is.
then. And I mean, it opens so many questions of how you manage to learn. I mean, even just like that, that there's more iron coming in from dust than from river sediments, just to try to conceptualize how you would set up a study to learn that, or what data you're using to. It sounds overwhelming.
Just another word with respect to the composition of ferromanganese crusts. There's also a water depth dependency. So crusts occur in water depths between around about 800 meter down to 4,000 meter water depth. They even occur in deeper water, but the formation process is even slower compared to the seamount. So as soon as there's hard rocks on the seafloor and no sediments, ferromanganese crusts also form in the deep sea. Even in 4,000 or 4,500 meter water depth, they can form there as well. But the growth rate is really very, very slow, maybe close to 1 millimeter per million years. Whereas on the seamounts, it is more the upper end of this 5-6 millimeter per million years. When we are close to mid-ocean ridges, where we have hydrothermal plumes with a lot of iron and manganese in it, the crust are also forming ferromanganese crusts, more with a hydrothermal hydrogenetic mixture. They have a higher growth rate. They can form up to several tens of millimeters per million years. But we are speaking on the seamounts. When we look at the seamounts, the seamount crusts grow on the processes I described, with the growth rate I described.
So the reason that when we're talking about mining seamounts, we're usually talking about shallower waters than mining nodules.
Yes, definitely.
Is because of the oxygen content of the water. That's the main reason that you have these crusts forming higher up in the water column, is because that's where the oxygen is in order for this oxidization process to happen.
Yeah, it is. It's because the oxygen minimum zone is so shallow. The oxygen minimum zone between 500 and 1,500 meter water depth occurs or forms when organic material which lives in the aquatic zone, in the surface waters, mainly phytoplankton and zooplankton, when it dies, it starts to move downwards through the water column.
Mm-hmm.
And then the organic material is oxidized. When it's oxidized, oxygen is consumed. And this is the reason why we have the oxygen minimum zone. It forms just underneath, starts forming underneath the aquatic zone. And it has its major depth between 500 and 1,500 meters. Depends a little bit on the amount of material, on the bioproductivity in the surface waters. So this is also changing, different, yeah. So it can be you can make it complicated as you want. Yeah. But okay, we have the seamounts, and what we also see, crusts that form maybe in 1,000 meter water depth. They are more enriched in manganese and elements associated with manganese, for instance, cobalt.
Okay.
And also most of the rare earth elements are enriched in the shallower crusts. When it gets deeper, the crusts get more and more enriched in iron compared to manganese, and the elements which are associated with iron, because this water depth dependency. And so the most interesting crusts are the shallower ones, so at around about 1,000 meter water depth. And so far, when it comes to mining, we are thinking about mining the transition from the summit areas to the flanks of the seamounts.
Okay.
And the upper flanks. But the upper flanks are the steepest parts of the seamounts. And as I showed in my presentation, these are also the parts of the seamounts which are subject to erosion, weathering, mass movement. So rather unstable areas.
Mm.
And we have now found during our cruise last year, When we look at the summit, it's the seamounts. The seamounts, they have been formed by volcanic processes, like Hawaii. Yeah, and many of these seamounts have grown from the seafloor until they form islands. Again, like Hawaii. When they form islands, they are subject to erosion. When the volcanic activity stops, then erosion takes over and flattens the island.
Right.
And then when the seamounts get older, they start to sink into the oceanic crust because they are getting heavier. They sink into the oceanic crust, and then they form seamounts. And these seamounts often, many of them have these kind of flat summit areas. They are called guyos. And they can be quite large. So we investigated a seamount with 600 square kilometer summit area.
Wow.
And this is flat, more or less rather flat, and only in 1,000 meter water depth. And most of the summit area is covered by sediments, but not all of it. And we now have found out that it may have something to do with currents that act on the sediments. But these currents are not only the currents which come from the deep, but these are currents which are caused by tides. And these tidal currents, at least in the seamounts we are investigating, are so strong that they really can move sediments. They can move sediments away from the summit area. And then you have a hard ground on the seafloor in the summit area, and you can form ferromanganese crusts. And ferromanganese crusts in 1,000 meter water depth on a flat seafloor are much easier to mine than on the flanks.
Right.
And that's why we say, look at the seamount summits. And I made an investigation in other areas, and I was talking to other colleagues like Bramley Merton on the conference, and he agreed. Yeah, they also found that the seamount summits are much more prone to ferromanganese formation than we previously thought. We previously thought that they are all covered by sediments, but this is not true. And when the summit areas are large enough, so for instance, this one seamount, 600 square kilometer summit area, 260 of this area, the summit, it's free of sediment. And we found many crusts there. And we made a calculation. We could have 12 million tons of crusts on this seamount alone. And this would contain round about 40,000 tons of rare earth elements. So in Germany, we import 5,000 tons of rare earth elements per year. So we could supply the German industry for 8 years completely with rare earth elements, only from this one seamount. So I think there's a significant potential for ferromanganese crusts on seamount summits. And this makes ferromanganese crusts much more interesting with respect to deep sea mining than previously thought.
And this is essentially new knowledge that...
Yes, I would say so. Yeah, because everybody, when I look into the literature, when I talk to colleagues, spoke about the flanks, to mine the flanks, and how to mine the flanks when they are so steep, and how we can do that. But I think this is not really necessary. We can look at the seamount summits, map the seamount summits, and I think not on every seamount, but on certain seamounts, there is a significant potential for the ferromanganese crusts. And we found crusts on a substrate which is called volcanic sandstone. It's an indurated sandstone, which is not very hard. So I think mining of this material could be very easy. Actually, you can just use a bagger or a grabber to mine this material. And even the sediments underneath have a certain amount of manganese. So they might even be interesting and not diluting the crusts. So I think seamount summits, we should be focusing much more on the seamount summits that we have done so far.
That's fascinating.
Yeah, this is something new. And there's another point with the crusts. In the geological history, there were phases with an increased bioproductivity in the surface water. And this caused the oxygen minimum zone to expand vertically and to be has a higher reducing state. this causes much more phosphorus to be dissolved in this oxygen minimum zone, and this phosphorus impregnated the crusts. So almost all of the ferromanganese crusts on the seamount summits have phosphor-rich layers in it. So the lower parts of these seamount, these ferromanganese crusts contain 5, 6, 7% of phosphor. So they are also a significant source for phosphor. Yeah, as everybody knows, phosphor is really needed for fertilizers, but also more and more for batteries. So when we look at these lithium iron phosphorus batteries, so we need phosphorus there as well. Yeah, so there is a competition between these different major users of phosphor, and the phosphor demand could also rise in the future. And so the crusts are also a significant source for phosphor. So it's a polymetallic source. Yeah? And with this new findings of a significant amount of ferromanganese crusts on seamounts, this shed a new light on the possibility to mine them.
It's so interesting to hear where the edge of kind of new science is.
Yeah.
And some of it is so surprising that it's something as simple as we didn't know that there were crust formations on the tops of these huge flat mountains. That it's fascinating to just learn where the gains are being made,
Yeah. And the other interesting thing in this respect, it's really a scientific topic. We cooperate with colleagues from the University of Bremen, who they did water column current measurements during our cruise last year with several different instruments. And an immediate or a first result of their investigations are these tidal currents over the seamounts, and they form kind of internal waves. And obviously, these tides, they can move the sediments on the seamount, and remove them from some part and maybe sediment them on other parts. And on the seamount summits, I said they are flat, but it's not quite true. Often on the seamounts, there's a late stage volcanic activity or a late stage period. So when the seamounts or when the volcanoes form islands, then the volcanic activity stops, erosion flattens the whole thing, and then in some cases there is a rejuvenated volcanic activity, a late stage volcanic activity when the seamount or the volcano is already flattened, and it forms cones on the seamount summit, small cones, a couple of 100 meters high, a few of them, and then it's only a very short volcanic episode, and then the whole seamount moves down, and it's volcanically dead. But these cones, they form obstacles called currents. And then in front of this, so on the loop side, there might strong currents removing sediments, and on the backside, you can deposit sediments. So this might control where we have crusts and where not. So I think the nice thing is really how different scientific topics, work together here. The geology, with the volcanology, erosion, tidal work, physics, sediment transport, and then chemistry during the formation of the crusts. So these different topics, they interact quite nicely. And this is also, I think, something rather new, I would say. It's not completely new. Our colleagues from Southampton, they published a paper going to the same direction, but I don't think they have spoken about the tides. So the tides that are these tidal effects. This is really something new, and the tidal effects you have since billion of years. So it's always there. Huh? So these tidal effects on sediment transport and sediment deposition or erosion, and then the formation of crust, these are working together, and this is something that has been working forever since Earth exists. Yeah,
fascinating, and it is it speaks to why these interdisciplinary research projects are necessary. It's interesting to hear
Yes.
because
Yeah.
often it feels like in the research world, like for some reason they want to force researchers to interact with one another.
Yeah.
And obviously there's kind of abstract gains there. So it's great to hear this is a very concrete example of how if we want to understand how and where the crusts form, you need
Yeah.
multiple different disciplines.
Right. Definitely. Yeah. Yeah.
Okay, is there anything else you feel is worth getting into on crust?
No, as I said, the economic potential of crusts is really big. So, for instance, in the West Pacific, this is an area where there are really many seamounts, and there are some resource estimations, and the amount of manganese, the amount of cobalt, is significantly larger in this area alone compared to what is known on land.
Yeah.
Only this area. So there's Seamount ferromanganese crusts have really a large potential for these critical metals that I mentioned. And we need to mine only a few of them. And of course, seamounts, with respect to the biology, seamounts are biological hotspots, or can be biological hotspots. Seamounts, in many cases, almost in the majority of cases, seamounts occur in chains.
Mm-hmm.
They form chains, like a pile of strings, just one after the other. And question is, when we look at them from a biological point of view, the animals living in one seamount, are they endemic or not? Or do we find them on the next seamount again? Yeah.
Right.
That if be able that the larvae move from one seamount to the other, they have to be connected hydrologically by currents.
Mm-hmm.
This is another objective of our project in the South Pacific, to investigate if seamounts are connected biologically or not, and under what circumstances. And so if we can prove that seamounts are connected, then if we mine on one side, on one seamount, the seamount can be re-inhabited from the neighboring seamounts. That should be made sure. Yeah. So this is something how we can make sure that that one seamount, when it comes to mining, is not completely devastated. Yeah. But even if we mine on one seamount, we will never mine a complete seamount. We only mine parts of it. Yeah. And we always make sure that the seamount can be restored, even if it takes time. Yeah. Longer time than in human timescales. But that it's principally most possible. That we should make sure when it comes to mining. And the same holds true for the manganese nodules or the massive sulfides, that within the natural timescales, the system can be restored. That's important, not within human timescales. That's my opinion. Maybe this is a message for the audience.
Interesting. And my understanding is that we are we as humanity are farther away from mining crust than nodules.
Yes.
Like there hasn't been any kind of tested mining systems that have kind of proof of concept.
Yeah, there were some tests by the Japanese.
Okay.
They mined 700 kilograms, something like this, with a mining vehicle. But that was all I know of. But I know that the Japanese, they are really pushing this marine mining topic in their EZ, in their exclusive economic zone. So, for instance, in January this year, there was a test mining on rare earth element rich deep sea mud in the Japanese EZ. And they also investigating and developing technology for massive sulfide mining nodule mining and crust mining. That's what they really push that, especially with respect to the crusts, because they are rich in rare earth elements. So ferromanganese crusts are really an source of rare earth elements, and that may be my last point. And not only on rare earth elements, but they always, in always all the cases, they have a certain amount of heavy rare earth elements. On land, most of the rare earth element deposits, and especially the ones in Europe, they're only rich in light rare earth elements like cerium, lanthanum, neodymium, and they are only the so-called iron adsorption clays in Southeast Asia, which are rich in heavy rare earth elements, the only ones. But the manganese crusts, they always contain between 10 and 30% heavy rare earth elements. So this makes them also interesting with respect to rare earth elements.
Between 10 and 30% of the rare earth elements that are contained in the crusts are heavies. That's what you mean?
Yes.
Yeah.
Right. So around most cases between 10 and 20%, but that's more than in most of the terrestrial deposits, which only contain the light earths. So this is another point which makes the crust interesting from an economic point of view.
Yeah, that's something that I think a lot of people kind of justifiably don't know about rare earths is that they this distinction between the heavies and the lights, and it's the heavies that really make the value.
Yeah.
I have one more question before we move on. One of the because manganese crust mining would happen in a shallower area, there would be more concern about the sediment plumes, I suppose, because they're in the more kind of biotically active area of the water column. And so what I've kind of heard is that, well, in nodule mining, they've kind of determined that you should put the return water deeper than 2,500 meters because there's very little life below that. But if you're mining up above 2,500 meters, then the plume is going to be at least more available to the life form. So I'm not sure if this is in your wheelhouse, but I wonder if you've got any insights there.
Actually, not really, because we are far away from developing this kind of crust mining technology. But what I can say, ferromanganese crusts would be mined in areas where there are no sediments.
Yeah,
so
interesting.
So I think the danger of producing sediment clouds is significantly smaller compared to manganese nodules. If there are sediments, they are rather coarse-grained because all the fine material is already moved away by currents. If there are sediments at all, but in most cases,
I imagine there would be sediments created from the mining process.
Yes, this might be the case. But I think not really. What you would produce are small pieces of rock. So what happens is you cut off the crusts on the seafloor, you move them to the vessel, and then in the vessel you would separate them from ambient rock, from ambient rock, and then you would transport these ambient rock back to the seafloor. So this ambient rock, this waste material would consist of pieces of rock actually, and they are not. They are probably in the size of maybe coarse sand or fine silt grain size. So they are large enough just to settle on the seafloor. It would not produce any plumes. The only thing that might be possible when you are close to the seamount slopes and you deposit these waste material at the edge of the seamount slope, then you could produce slumpings. Material moving down on the slope of the seamount. One should make sure that you deposit the material on the top of the seamount. If the seamount is large enough, that shouldn't be a problem. Otherwise, one should make sure that the material is stayed on the vessel and maybe transported ashore and deposited somewhere there. Yeah. So, but I think a plume would. I don't think that the plume is a problem. But the problem would be how to deal with the waste material, with the rather coarse-grained waste material, and making sure that you don't produce slumpings, which run
Interesting.
down a seamount slope and then could impact a larger area. That's true.
I just don't naturally realize when thinking about sediments
Right.
is the distinction between a coarse grain and a fine grain and things like that.
Yeah.
So that's
Yeah.
interesting. Okay, well then let's transition. I mean, I'm a little bit tempted to follow up on one of the things you said there about the freedom of expression and how people are speaking openly about things and try to make a somewhat forced connection to the deep sea mining conversation. But let's talk about deep sea mining. So you've been in this field now for quite a long time, from a number of different directions. So yeah, I guess let's just start if you've got kind of like a message so people who listen to this audience are interested in deep sea mining, but they come from a lot of different perspectives. I try to make this appeal to kind of everyone from all camps. So just for the people who are only going to listen to the opening section, what kind of take-home message would you like to leave them with?
Yeah. Okay. We talk about deep sea mining. Deep sea mining means excavation of certain minerals which contain certain metals, and it's mainly about the so-called critical raw materials or critical metals, which are supposed to be critical in a certain way for our society. We mainly speak about metals like cobalt, nickel, copper, rare earth elements, and things like that. The first thing I want to say is, with respect to the change of our society to a net zero society, or to say at least a net zero industry, we should agree upon that there is a growing demand on these critical metals because of the actual technologies that we are using for this energy change. When we agree on that, I also often hear the argument that we can cover this growing demand by growing recycling. And so my first message is that I think there's a growing demand on these metals. Second message would be, we cannot cover this growing demand by recycling because there is just not enough of this material in the loop. So that's why we need additional critical metals which have to come from somewhere. They come from mining, actually. With deep sea mining, we could cover, at least to a certain degree, this additional demand, which would reduce the pressure on the terrestrial deposits, and which can reduce our dependency on certain producers, mainly China, but also Russia, for instance. So this would be the third message. And the fourth major concerns with respect to deep sea mining are environmental impacts on the deep sea ecosystem. This is true. There will definitely are impacts. But here we have to consider two major points. First, when we do terrestrial mining, there's an impact as well. So we have to kind of compare these impacts. I know this is difficult, but at least we have to accept that there are on both sides there are impacts. And the second point with the deep sea mining, we should also consider that there are natural fluctuations and there's a natural variability of this ecosystem. So the ecosystem is not a stable one which doesn't change. And I have the impression that sometimes this is something it is suggested, but this is not completely true. We have these, or there are these natural changes. For instance, in the Klein-Clipperton zone, we have significant erosion on the seafloor caused by natural processes. There are earthquakes which cause slumpings which cause mass movements on the seafloor. We have, because of these mass movements, nodules can be covered or the cover can be removed, and the ecosystem is able to adapt to these changes. Maybe on a time scale which is not human, maybe which is longer than a human time scale, but these adaptations are ongoing, and we have to take into account these natural variability and ask ourselves if the impact that we cause by deep sea mining, to put it in a different way, we should make sure that the impacts of deep sea mining are within this natural variability. If we can make sure that this happens, then I think deep sea mining is really not an alternative, but an additional source for critical metals, and we should really put that into our decision making. So these are the four messages. Maybe it was a little bit too long, but I hope
interesting. And so, I mean, the first three messages there I hear a lot, and I think that's very central to the deep sea mining discussion. I think it's interesting that, I mean, I assume that you still feel that those messages are not sufficiently understood, that we need the metals, or we have the demand for the metals. I mean, need and having demand, I guess, are two different things. People would say we should reduce our demand, but we have this demand for the metals, and that, recycling isn't an option. And you feel like that in the deep sea mining conversations that you're very much a part of, you feel like that isn't kind of accepted, or we're spending too much time on that part. Is that right?
Yeah, maybe one thought I would like to add. When we think about the demand, we only think about our demand in the Western world, but you should take into account that in the developing countries, what you need there is not the sophisticated. Maybe you also need the laptops and windmills and things like that, but they need roads, they need buildings, they need just the basic things. And within these basic things, in each case, you need these critical metals. So it's not only for this net zero change that we do, or that maybe the entire world will do, but in the developing countries, which is the majority of the world, there's a significant demand for just the basic infrastructure. And for this basic infrastructure, you also need this kind of metals. And this is the reason why we have this tremendous increase in demand. And there was a recent publication by Greenpeace, and they just neglect that. They just they base their whole calculations on, in my opinion, to numbers which are far off the reality. It's wishful thinking to my understanding, and that's why there are so many studies from industry, but also from academia, from politics, that prove this increasing demand of metals. That I think it should be clear, but no, it's not clear. When I look at the Greenpeace study, for me, obviously it's not clear, and that's why we have to repeat that again, even if it's something which seems to be rather simple.
Interesting. Okay, well, that's great. That's exactly the level of detail that I was hoping. For people who've listened to this, they have a lot more of the context around whether there's a concern and in what situations you need to take precautions, et cetera, et cetera. So that's great. Thanks very much. I'll put links to this publication in the show notes. And if there's any other of the publications around the crust formation that you think are interesting, we can link to those also.
Okay.
Is there anything else you would like to mention before we wrap up?
No, I'm fine. I mean, there are many more details with respect to the crusts or the nodules, but I think we provided a nice overview.
I learned a lot, and I imagine that listeners will appreciate learning it also. Thomas, thanks very much for your time, and nice talking with you.
Yeah, it was nice having me here, and I appreciate it, and I enjoyed it. Thank you very much.